Welcome! In this session, we'll explore an exciting problem, number 673, number of longest increasing subsequence. We'll break down the problem, analyze various approaches, and understand the optimal solution. Let's dive in. In this problem, we're tasked with finding the number of longest increasing subsequences in a given array of integers, nums. A subsequence is a sequence that can be formed by deleting some or no elements from the array, while still maintaining the order of the remaining elements. For example, 3, 6, 2, 7 is a subsequence of 0, 3, 1, 6, 2, 2, 7. A sequence is considered increasing if each subsequent number is strictly greater than the previous one. The longest increasing subsequence is the one with the maximum possible length among all increasing subsequences in the array. Our goal is to determine how many such longest increasing subsequences exist. The input to this problem is the integer array nums, and the output is an integer representing the count of these subsequences. For example, if the input array is nums equals 1, 3, 5, 4, 7, the output will be 2. This is because the array has two longest increasing subsequences, 1, 3, 5, 7, and 1, 3, 4, 7. Both of these subsequences have a length of 4, which is the maximum possible length for this array. Another example is nums equals 2, 2, 2, 2, 2. In this case, the output is 5, as each individual 2 forms a subsequence of length 1, and there are no longer increasing subsequences. Since all elements are the same, there are 5 such subsequences, one for each index in the array. Consider the input nums equals 1, 2, 4, 3, 5, 4, 7, 2. Here, the output is 3. The three longest increasing subsequences are 1, 2, 3, 5, 7, 1, 2, 4, 5, 7, and another 1, 2, 4, 5, 7, formed from different indices. These subsequences all have a length of 5, which is the maximum possible for this array. The constraints for the problem are important to note. The length of the array can go up to 2000, and each element can range from -10⁻6 to 10⁻6. These constraints mean we need to design an efficient solution that handles large input sizes and edge cases effectively. To build a solution, we must consider some key points about the constraints. First, the array length of up to 2000 means that solutions with a time complexity of O(n) cubed will be too slow. Instead, we should aim for approaches with a time complexity closer to O(n squared). Second, while the range of values in the array is large, the problem itself focuses on finding subsequences, so the range doesn't directly affect performance. Finally, we need to handle edge cases, such as arrays with a single element, arrays where all elements are the same, arrays in strictly increasing order, and arrays in strictly decreasing order. These scenarios ensure our solution is robust and can handle all possible inputs efficiently. To tackle the problem, let's first consider the brute force approach. Here, the idea is to generate all possible subsequences of the given array. Then, we check which of these subsequences are strictly increasing and determine their lengths. Once we identify all the longest increasing subsequences, we count how many of them exist. However, this method has significant drawbacks. Generating all subsequences for an array of length n involves 2⁻n possibilities, making it computationally expensive. On top of that, verifying whether each subsequence is increasing adds more complexity. As a result, this approach quickly becomes infeasible for larger input sizes due to its exponential time complexity, with a time complexity of O(2 to the power of n, and space complexity of O(n), to handle the recursion stack. To address these inefficiencies, we turn to dynamic programming, which offers a much more optimized solution. The key idea here is to use two arrays, dp, I, to track the length of the longest increasing subsequence ending at index I, and count, I, to store the number of such subsequences for that index. With dynamic programming, we observe that for each index I, we need to check all previous indices j where nums, j, is less than nums, I. If adding nums, I, to the subsequence ending at j results in a longer subsequence, we update dp, I, to dp, j, plus 1 and reset count, I, to count, j, since all the longest subsequences at j now contribute to I. On the other hand, if the subsequence length remains the same, that is, if dp, j, plus 1 equals dp, I, we simply increment count, I, by count, j. After processing all indices, the length of the longest increasing subsequence is the maximum value in the DP array, and the total number of such subsequences is the sum of the corresponding values in the count array. The beauty of this approach lies in its efficiency, as it combines the computation of both LIS length and count in a single nested loop. This gives us a time complexity of O(n) squared, with space complexity of O(n) for storing the DP and count arrays. For larger arrays where nums spans a wide range, an alternative optimized approach involves using a binary index tree, bit, with coordinate compression to achieve O(n) log n time complexity. Despite the faster theoretical performance of the bit approach, we focus on the O(n) squared dynamic programming solution for its simplicity and practicality. While the bit method is more efficient for very large ranges, it requires additional pre-processing steps like coordinate compression and is more challenging to implement. In contrast, the O(n) squared DP approach strikes a good balance between clarity and performance, making it well suited for most LeetCode constraints. When comparing approaches, the brute force method is clearly impractical due to its exponential complexity. The bit approach is faster but involves a steeper learning curve and is unnecessary for typical input sizes. Thus, the O(n) squared DP solution is the best choice given its manageable complexity and ease of debugging. This gives us a final complexity of O(n) squared, 4 times an O(n) for space, making it both efficient and accessible for this problem. In this problem, we are tasked with finding the length of the longest increasing subsequence, or LIS, in a given array of integers, as well as counting how many such subsequences exist. To clarify, a subsequence is a sequence that can be derived by deleting 0 or more elements from the array without reordering the remaining elements. For example, in the sequence 1, 3, 5, all elements are in a strictly increasing order, meaning each number is greater than the one before it. Our goal is twofold: first, to compute the length of the LIS, and second, to count how many distinct subsequences achieve this maximum length. To solve this efficiently, we use dynamic programming with two key data structures. The first is an array DP, where DP, I, represents the length of the longest increasing subsequence that ends at index I. The second is an array count, where count, I, tracks how many such subsequences of maximum length exist at index I. These two arrays work together to help us calculate the solution efficiently while avoiding redundant computations. To implement the algorithm, we start by initializing the base cases. For every index I in the array, we set DP, I, to 1, because the minimum length of an increasing subsequence at any index is 1, consisting of the element itself. Similarly, we set count, I, to 1, as there is at least one subsequence ending at I, which is the element itself. Once the base cases are set, we iterate through the array from left to right. For each index I, we compare the value of nums, I, with all previous elements in the array, denoted by nums, j, for indices j ranging from 0 to I1. If nums, j, is less than nums, I, it means we can extend the increasing subsequence ending at j to include I. In this case, we update dp, I, to be dp, j, plus 1 if this new length is greater than the current value of dp, I. At the same time, we reset count, I, to count, j, as we are inheriting the number of subsequences from index j. If the length dp, j, plus 1 is equal to dp, I, we add count, j, to count, I, meaning we are combining counts from multiple sources. On the other hand, if nums, j, is greater than or equal to nums, I, we simply skip that index and continue. Once we have processed the entire array, we can extract the results. The length of the longest increasing subsequence is simply the maximum value in the DP array, which we calculate as max, DP. To count the number of such subsequences, we sum up all the values in the count array for indices where the DP value is equal to the maximum LIS length. This ensures that we only include the counts for subsequences that achieve the desired length. There are several key insights to keep in mind for this algorithm. First, brute force approaches that generate all possible subsequences would be computationally expensive due to their exponential complexity, but dynamic programming allows us to avoid redundant calculations. Second, the count array is critical for efficiently tracking the number of LIS at each index without needing extra traversals. Third, the transition relation ensures correctness by extending valid subsequences from earlier indices to the current index. Lastly, we handle edge cases like single-element arrays, arrays with all identical values, and strictly increasing arrays by design, ensuring the algorithm works universally. The algorithm relies on two primary data structures, the DP array and the count array. Both are space-efficient, requiring only O(n) memory. The DP array stores the LIS lengths at each index, while the count array tracks the number of subsequences corresponding to those lengths. Together, they allow us to iteratively update and compute the required values. The core computation is managed through two nested loops. The outer loop iterates over the array with index I, representing the current element we are processing. The inner loop iterates over all previous indices j, checking whether the value at j can extend the LIS ending at I. This nested structure gives the algorithm a time complexity of O(n squared), as each pair of indices is considered once. However, the space complexity remains O(n), as we only use the DP and count arrays to store intermediate results. This balance of time and space efficiency makes the algorithm well-suited for mid-sized input arrays. To solidify our understanding, let's walk through an example with the input array nums equals 1, 3, 5, 4, 7. Initially, we set DP equals 1, 1, 1, 1, 1, and count equals 1, 1, 1, 1, 1, since each element starts as its own subsequence. For I equals 1, comparing with j equals 0, the value 3 extends the subsequence ending at 1, so we update DP 1 to 2 and keep count 1 as 1. For I equals 2, comparing with j equals 0 and j equals 1, the value 5 extends the LIS to length 3, so DP 2 becomes 3 and count 2 remains 1. For I equals 3, the value 4 extends the subsequence from j equals 0 and j equals 1, updating DP 3 to 3 and count 3 to 1. Finally, at I equals 4, the value 7 extends subsequences from both j equals 2 and j equals 3, resulting in DP 4 equals 4 and count 4 equals 2. The maximum LIS length is 4, and there are two LIS of this length. Thus, the final output is a length of 4 and a count of 2. This Python implementation solves LeetCode problem number 673, number of longest increasing subsequence. The goal is to find the number of longest strictly increasing subsequences in a given list of integers. Explanation. 1. Base case. First, the function checks if the input list nums is empty. If it is, there are no subsequences, so it returns 0. 2. Initialization. Lengths. An array where lengths I represents the length of the longest increasing subsequence ending at index I. It is initialized to 1 for all indices, as every single element is a subsequence of length 1. Counts. An array where counts I represents the number of longest increasing subsequences ending at index I. It is also initialized to 1, as there is initially one subsequence, the element itself, for each index. 3. Nested loops. The outer loop iterates over every index I in the array. The inner loop iterates over all indices j before I. If nums j nums I, it means the element at I can extend the subsequence ending at j. If lengths j plus 1 is greater than lengths I, it means a longer subsequence is found. Update lengths I, and reset counts I to counts j. If lengths j plus 1 is equal to lengths I, it means another subsequence of the same maximum length is found. Add counts j to counts I. 4. Final calculation. After the loops, find the maximum length of increasing subsequences using max lengths. Sum up the counts of all indices where the LIS length equals the maximum length. 5. Return result. The function returns the total number of longest increasing subsequences. Complexity. The time complexity is O(n squared, due to the nested loops. The space complexity is O(n), for the lengths and counts arrays. This approach efficiently calculates the desired result while handling edge cases like empty input or arrays with all identical elements. Here, we start by defining our solution class and the method findNumberOfLIS, which takes an array of integers nums as input. The first thing we do is check if the array is empty, and if so, we return 0, as there are no subsequences to evaluate. Next, we declare two arrays, lengths and counts, both of size n, where n is the length of the input array. The lengths array keeps track of the length of the longest increasing subsequence ending at each index, while the counts array keeps track of the number of such subsequences. Both arrays are initialized to 1, as every individual element is an increasing subsequence of length 1 by itself. We then use two nested loops to iterate through the array. The outer loop runs through each index I in the array, while the inner loop checks all indices j that come before I. If nums, j, is less than nums, I, we know we can form a longer increasing subsequence by appending nums, I, to the subsequence ending at j. If the new subsequence length is greater than the current value in lengths, I, we update lengths, I, and reset counts, I, to counts, j, as this is now the only way to achieve this new length. If the new subsequence length equals the current value in lengths, I, we add counts, j, to counts, I, as there are now additional ways to form subsequences of the same length ending at I. Now that we've processed all pairs of indices, the next step is to determine the maximum length of the longest increasing subsequence. We initialize a variable max length to 0 and iterate through the lengths array, updating max length to the highest value encountered. This gives us the length of the longest increasing subsequence in the array. Finally, we calculate the total number of such subsequences by iterating through the array again. For each index I where lengths, I, equals max length, we add counts, I, to a variable result. This ensures we sum up all the counts of subsequences that achieve the maximum length. At the end, we return result, which represents the total number of longest increasing subsequences in the input array. To solve this problem, we start with the array nums equals 1, 3, 5, 4, 7. The first step is to initialize two arrays. The lengths array keeps track of the length of the longest increasing subsequence, LIS, ending at each index, and the counts array tells us how many such subsequences exist. Initially, each element in nums forms its own subsequence of length 1, so lengths and counts are both set to 1, 1, 1, 1, 1. Next, we iterate through the array to compute the LIS. For I equals 1, where nums, I, equals 3, we compare it to all previous elements. Comparing with j equals 0 where nums, j, equals 1, since 1, 3, we update lengths, 1, to lengths, 0, plus 1, which is 2, and set counts, 1, to counts, 0, which remains 1. At this point, the updated state becomes lengths equals 1, 2, 1, 1, 1, and counts equals 1, 1, 1, 1, 1. For I equals 2, where nums, I, equals 5, we compare it with all previous indices. Starting with j equals 0 where nums, j, equals 1, since 1, 5, we update lengths, 2, to lengths, 0, plus 1, which is 2, and set counts, 2, to counts, 0, which is 1. Next, comparing with j equals 1 where nums, j, equals 3, since 3, 5, we update lengths, 2, to lengths, 1, plus 1, which is 3, and set counts, 2, to counts, 1, which remains 1. This gives us the updated state lengths equals 1, 2, 3, 1, 1, and counts equals 1, 1, 1, 1, 1. Now, for I equals 3 where nums, I, equals 4, we again compare with all previous indices. For j equals 0 where nums, j, equals 1, since 1, 4, we update lengths, 3, to lengths, 0, plus 1, which is 2, and set counts, 3, to counts, 0, which is 1. Comparing with j equals 1 where nums, j, equals 3, since 3, 4, we update lengths, 3, to lengths, 1, plus 1, which is 3, and set counts, 3, to counts, 1, which remains 1. Finally, with j equals 2 where nums, j, equals 5, since 5, 4, no update is made. The state becomes lengths equals 1, 2, 3, 3, 1, and counts equals 1, 1, 1, 1, 1. Now for I equals 4 where nums, I, equals 7, we compare it with all previous indices. Starting with j equals 0, j equals 1, j equals 2, and j equals 3, we find that each of these elements is less than 7, so we update lengths, 4, to the maximum LIS found, which is 4. Additionally, there are two ways to achieve this LIS ending at index 4, so counts, 4, becomes 2. The final state of the arrays is lengths equals 1, 2, 3, 3, 4, and counts equals 1, 1, 1, 1, 2. At this point, we compute the result. The maximum length of any LIS is 4, and the total number of such subsequences is the sum of counts where lengths, I, equals 4, which gives us 2. Therefore, the output for this example is 2. In example 2, we consider nums equals 2, 2, 2, 2, 2. Once again, we start by initializing the lengths and counts arrays to 1, 1, 1, 1, 1. Since all elements are equal, no element can form an increasing subsequence with another. This means there are no updates to the lengths or counts arrays during the iteration. The final state remains lengths equals 1, 1, 1, 1, 1, and counts equals 1, 1, 1, 1, 1. To compute the result, we observe that the maximum length of any LAS is 1, and the total number of such subsequences is the sum of counts where lengths I equals 1, which equals 5. Thus, the output for this example is 5. In example 3, we consider nums equals 1, 2, 4, 3, 5, 4, 7, 2. As always, we begin by initializing lengths and counts to 1, 1, 1, 1, 1, 1, 1, 1. Following the same process of comparing each element with all previous ones, we dynamically update the lengths and counts arrays. After completing the iteration, the final state is lengths equals 1, 2, 3, 3, 4, 4, 5, 2, and counts equals 1, 1, 1, 1, 2, 1, 3, 1. The maximum length of any LAS is 5, and there are 3 such subsequences. This is calculated by summing the counts where lengths I equals 5. Therefore, the output for this example is 3. To analyze the time complexity of the solution, we start by examining the structure of the loops. The outer loop, referred to as the I loop, iterates through every index in the input array nums. Since this loop processes each of the n elements exactly once, it contributes n iterations. Inside this outer loop, we have an inner loop, known as the j loop, which evaluates all indices j that are less than the current index I. For the ith iteration of the outer loop, the inner loop will run up to I1 times in the worst case. Within this inner loop, we perform constant time operations, such as comparing values and updating the lengths and counts arrays. These constant time operations are O1. Therefore, the overall cost of each iteration of the inner loop depends on how many times it runs, which we will analyze mathematically in the next step. Now, let's derive the total number of iterations performed by the nested loops. For the first value of I, when I equals 0, the inner loop does not execute at all, resulting in 0 iterations. For I equals 1, the inner loop runs once. For I equals 2, it runs twice, and so on. By the time I reaches n1, the inner loop runs n1 times. If we sum the iterations across all values of I, we get a series 0 plus 1 plus 2 plus n1. Using the formula for the sum of the first n1 integers, this evaluates to n asterisk n1/2, which simplifies to n squared. Additional operations like computing the maximum length of the subsequence and summing the counts both require n time, but these are negligible compared to the n squared contribution from the nested loops. Therefore, the overall time complexity of the solution is n squared. Turning our focus to space complexity, the input array nums itself does not count as additional space since it is part of the given input. The main contributors to space usage are 2 auxiliary arrays, lengths and counts. Each of these arrays has a size equal to the length of nums, which is n. Thus, the space required for these arrays is n. Beyond these arrays, we only use a few scalar variables, such as max_length and the loop counters, which take up constant space, or O1. Combining these factors, the total space complexity of the solution is n, as the auxiliary arrays dominate the overall space usage. To better understand the efficiency of this solution, we can analyze the best, average, and worst cases. Interestingly, the time complexity remains n squared in all cases because the nested loops always iterate in the same pattern. However, the number of operations within the inner loop can vary. In the best case, where the input array is sorted in descending order, no updates to the lengths or counts arrays occur after initialization, minimizing the work done inside the inner loop. In the average case, the operations depend on the specific distribution of values in the array, but the overall complexity remains n squared. The worst case happens when the array is sorted in ascending order. Here, each element contributes to an increasing subsequence, leading to updates in both lengths and counts during every inner loop iteration, maximizing the number of operations. Compared to a brute force approach, which would involve generating all 2 and possible subsequences and checking each one. This dynamic programming solution is vastly more efficient, reducing the time complexity to O(n squared). Finally, let's mathematically justify the big O notation for this solution. The nested loops are the dominant factor in the time complexity, and we've already derived that the total number of iterations is given by the summation formula n*(n1/2). This simplifies to O(n squared). As for space, the auxiliary array's lengths and counts scale linearly with the size of the input, contributing O(n) space. Combining these observations, the time complexity is O(n squared, and the space complexity is O(n). This solution is optimal within the constraints of the problem, as reducing the time complexity below O(n squared would require fundamentally changing the approach, which might compromise correctness. Thus, this dynamic programming approach strikes a balance between efficiency and accuracy. When solving the number of longest increasing subsequence problem, there are several common mistakes to watch out for. First, failing to handle edge cases like empty arrays or single-element arrays can lead to runtime errors or incorrect results. For instance, an empty array has no subsequences, so the expected output should be 0. Overlooking this check might cause index-related errors in your code. Another frequent mistake is confusing subsequences with subarrays. Remember, a subsequence can be formed by removing 0 or more elements without changing their order, while a subarray must always be contiguous. Misunderstanding this distinction can lead to faulty logic. Additionally, relying on brute force approaches with nested loops is inefficient. Generating all possible subsequences involves 2 to the power of n combinations, which becomes computationally prohibitive for large inputs. Finally, ensure that comparisons in strictly increasing sequences are handled correctly. Specifically, you must verify that each element in the sequence satisfies the condition where a_i is less than a_j for indices I less than j. Neglecting this can result in invalid subsequences being included in your solution, leading to logical errors. Another mistake to avoid is overlooking memoization in dynamic programming solutions. Without memoization, you might end up recomputing overlapping subproblems, significantly increasing the time complexity. For example, an algorithm that could run in O(n squared might degrade to something far less efficient without proper memoization. On the interview side, it's crucial to clarify the difference between subsequences and subarrays at the outset. This distinction is a common interview question and sets the foundation for your approach. Additionally, focus on optimizing for efficiency. While brute force solutions can show initial understanding, aim to discuss better approaches like dynamic programming or even binary search methods. Be prepared to discuss spacetime trade-offs too. For instance, a dynamic programming approach with O(n squared time and O(n) space is standard, but you can also explore O(n log n) solutions using binary search. Finally, always explain your thought process clearly. Even if you don't immediately land on the most efficient solution, articulating your reasoning demonstrates strong problem-solving skills, which is often more important than the final answer in an interview setting. This problem is closely related to several others that you might encounter, which can help deepen your understanding of subsequences. The longest increasing subsequence problem, LeetCode 300, is foundational. It focuses on finding the length of the longest strictly increasing subsequence in an array. The current problem, number of longest increasing subsequences, builds on that by counting all such subsequences of maximum length. Another related problem is longest common subsequence, LeetCode 1143, where the goal is to find the longest subsequence common to 2 strings. This introduces the idea of comparing 2 sequences rather than just analyzing one. Finally, there's the increasing triplet subsequence, LeetCode 334, which is a variation where you're tasked with determining if there exists a subsequence of length 3 within the array. These problems share overlapping concepts, and studying them can give you a broader perspective on how to approach subsequence-based challenges. There are several alternative approaches to solving this problem, each with its own trade-offs. The dynamic programming approach, which runs in O(n squared time, relies on a DP array where DP I represents the length of the longest increasing subsequence ending at index I. For each index, you update DP I by checking all prior indices where the condition I is satisfied. This method is relatively straightforward to implement, but its quadratic time complexity can be slow for larger inputs. A faster option is the binary search approach, which achieves n log n time complexity using a technique inspired by patience sorting. Here, you maintain an auxiliary array to track the smallest possible tail values for increasing subsequences of different lengths. Binary search allows you to efficiently replace elements in this auxiliary array. While this method is faster, it can be harder to implement and explain during interviews. Another option is to use recursion with memoization. This approach explores all possibilities recursively while caching previously computed results to avoid redundant calculations. It's often easier to derive but may still be slower compared to iterative dynamic programming for larger inputs. Each method has its strengths, and the choice depends on the specific constraints and context of the problem. Great work! Today, we tackled the problem number of longest increasing subsequence and explored how dynamic programming can efficiently solve it. Remember to apply these concepts to similar problems to strengthen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!